In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science.
All right, hello and welcome everyone to Celestial Theodolite episode number 12. We're going to get into an overview of the Celestial Theodolite itself, methodology, process, and all that. And then we'll get into an open Q&A. All right, so to start us off here, I'll do a little screen share, cover some of the finer points of the Celestial Theodolite, and then we will get into Q&A. Just changing resolution here. Okay, make selection. There we go. All right, I have a screen share up if you guys are able to join that now. Okay, so the basic concept for the Celestial Theodolite is you can record star occlusions or emergences when the star appears or the moment that it disappears. And you can go into Stellarium and reference the true position of the star and see if it lines up with the calculated value for the angle to the peak that that's doing the occluding or the emerging. So if you're an observer on the ground and you're, let's say 50.7 kilometers away from a peak, and you do a little trig on the distance and the difference in elevation between you and the peak, you can get the angle, just the raw angle, no refraction or anything like that. And then you can also from that, you could subtract what the difference would be for the globe Earth prediction for 8 inches per mile squared. And with that, you can have two mutually exclusive angles that correspond to different times, because if you guys aren't familiar, the globe model is entirely based upon latitude and longitude, which is based on the positions of the stars with respect to time. So if there's a time, that corresponds to an angle, and if there's an angle, that corresponds to a time, vice versa, right? So we can backwards derive the two. And we have, and because we know occlusions are a physical process, which we'll get into in a second, the outcome of the occlusion angle will determine the physical elevation of the mountain. And taking it a step further, once we have the angle and the distance, we can backwards derive what the elevation of the mountain is, doing a further analysis on it. All right, so to continue on here, we're going to look at an example from Taylor, who is using a laser and a knife inside of a cup full of water. And this is going to be an example of a refracted image not being able to occlude refracted light. There has to be a physical intersection with the source and the physical knife that's in the water. So you'll see here, when I play this video out, you'll see when it's interacting with the refracted image of the knife, it shines through it. There's no occlusion, and not until the laser pointer is moved to the physical intersection with the knife is when it gets blocked. And to give a more refined example of that, we have a video demonstration from Goose, and you can watch the full video and an explanation on Celestial Theodolite Update 10. But I'm going to give a quick overview here. So the basic premise of this is he comes up with this rig here, and he's got two dowels. One is going to be our observer. There's going to be a camera here, and there's a point source of light over here. There's a dowel in the middle. This dowel is going to be aligned with a stick here, so we can see that when there's no refractive medium between the light source and this dowel here, that the light source is right next to the stick. Now, obviously, there's a little bit of refraction, but it's so minuscule at this distance, and with just regular air temperature, etc., it's basically negligible, right? So this is just demonstrating the occlusion from this observer here when there's nothing in between the observer and the mount, or in this object to occlude it. The physical occlusion happens right here, right? You can see this is lined up with the stick, keeping it all straight there. And then when he adds a medium between the light source and the thing doing the occluding, what we're going to notice is that the physical intersection point changes. So even with refraction, right? If you account for refraction on one end of this, then that's all that there's still going to be a mutually exclusive outcome for the occlusion. It still dictates a different timing, because when he adds this stick here, you'll see now that the physical occlusion point has changed for this observer over here. And this does not correspond to the full entire angle of the refracted index, right? That would be preposterous. That would be, because this is just a little tiny dot. Like, it can't be way under the other side of it physically and still be refracted over it. Once it crosses that threshold on this side of the refractive index and it's actually physically occluded, then this observer no longer sees it. So the idea that stars, which are about an arc minute, maybe an arc minute and a half in size, are being lifted up 20 to 25, almost 30 arc seconds to still be visible over a mountain is preposterous. So one thing on occlusions that's super important, we know occlusions are a physical process, and this is really important because we're told the story that you used to be able to determine, well, you still can apparently, but you could determine your longitude through the eclipse cycle of Jupiter's moons. And you could, and through that process, right, it's timing specific. So when the moon's no longer visible versus when the moon reemerges, that's when you take your timing differences to determine which longitude you're at, because that's going to determine the timing difference from that when they occlude and emerge is going to determine your longi when you would see that. So with that process, right, in quote unquote space, right, there's no medium, no refractive index between the two. So this moon is, conceptually, right, this moon is being occluded by another physical object, and it's not visible anymore. There's no refractive corrections or anything like that. So when you go to determine your longitude, making the observation, you don't add any refractive, anything like that for that. So it's clearly a physical process that that does the occlusion and stops the observer from being able to see the light. So a big part of this argumentation is that, we don't account for refraction in the calculations, but that's for a very specific reason. It doesn't change the outcome of which time the star would stop being visible. Well, it changes it, but not to the degree where we would have a situation where it's going to be well behind the actual physical object and it's still going to be visible, right? That's not what happens. As soon as that actual intersection happens with respect to the side that is being refracted, it's physically occluded for everyone on the other side, especially when you're dealing with a point source here. So, all right. Let me check my notes real quick. There was a couple other things I wanted to go over. I had to reboot before I went live here. Sorry about that. All right. Yeah. Regarding fictitious observers. Okay. So another big argument against the celestial theodolite is that we're moving the observer to where he isn't and all this stuff. No. So what's happening here, right? The process of how this works is you see a peak, see a mountain range, ridge or peak, whatever, right? You look up what that peak is, and you calculate the distance between you and the peak using whatever website you prefer. You can use movable types. You can use NOAA, doesn't matter. It'll give you a distance. And from that, we go to the mountain peak in Stellarium, and we look for stars that are at the same relative angle that we just calculated. And when the true position of that star, the unrefracted position of that star, is intersected with that angle, we just write down what time that is. And if we go out at our location that we calculated that relative angle to, the globe would predict that there's no geometric physical connection between that observer and that starlight. Because if you go to Stellarium, enter the observer coordinates, the star is going to be well below the true position, is going to be well below the mountain peak. And it may be refracted up close to or just above the peak, but it doesn't. But it's not visible at that time, and it's only visible, and it becomes no longer visible when the true position is intersected at the same angle as where it would be as if it was observed from the peak, which is a geometric relationship that should not happen on a globe. We are testing the model. We are not doing anything dubious or weird or moving the observer where it's not. And it's extremely important to understand the implication of moving the observer where he's not, because the entire globe model, latitude and longitude, is based on a snapshot of the positions of the stars where people took zenith measurements on the vernal equinoxes, and they stitched those together with a geocentric coordinate transformation, which is setting those observers to the center of the terrestrial sphere, and then setting the elevation of that star to what would be 3959, so that it will share the 69 mile per degree relationship when it's observed through the angles of 25 to 70 degrees. And that is what makes up the model there. It's all tied together via the fictitious observer, so that you could calculate where the angle to the star would be with respect to time. Because if you know where the star once was at the vernal equinox, well, calculating 15 degrees per hour and then adding your local time to it, you can figure out where, what angle that's going to correspond to and what time that star is going to be at that angle. So the whole model is based off of moving the observer where he's not. And this is called the geocentric position. It's referenced in celestial navigation, the almanacs. It's how you make use of the latitude longitude system. So there's no room to point fingers here. If you're a globularist, your model is entirely based on comparing your position on the ground to a fictitious observer, and using that as the reference. So now when we get into fudge factors, right? Because there's been some talk of, is the current analysis method just a fudge factor, et cetera, et cetera? Well, even without the current analysis, which we'll get into in a second, we don't need any quote unquote fudge factors. But while we're on the subject of fudge factors, with the sky moving at 15 degrees per hour to make use of the coordinate system to relate angles and time to positions on the ground, when the stars get close to the horizon, they don't obey the 15 degree per hour relationship. Therefore, their angle and timing wouldn't make sense to the 15 degree per hour. So they have to be refracted up in a way that keeps them coplanar, so that their angle still relates to a geographic position with respect to the time that the angle is observed. And the way that they came up with the celestial refraction corrections was by taking real world observations and then just curve fitting them to what the globe would have to have for, in terms of how much refraction would have to be there to make it fit. They just force that in there, and then from that curve fit, they get coefficients that they're able to apply to the observing angle. So you get this output of this weird number string that you have to multiply by your angle squared or cubed even, and that little adjustment there gives you the necessary 20 to or 15 to 20 some arc minutes of refraction to put that star where it needs to be. And there's no, that's not derived off of any first principles or anything. You can look up using the Supplemental Nautical Almanac as your reference for where they talk about where the refraction calculations are tabulated from, where they're derived from, how they're used and whatnot. They give a nice source list here. When you go through this, what you'll find is that all those coefficients are derived from computational models that are where the input is the globe, so the output is obviously going to be the globe, and it's just curve fitting to what it has to be. So like it's the ultimate unfalsifiable, correction to apply. It makes it pretty much unfalsifiable in that regard. So when we're talking fudge factors, that's like an actual fudge factor. That's not what's happening here or what's necessary here. And there are two other observations that are in question. And one is the Greenhorn Mountain observation, where the star was occluded at an elevation that would correspond to about 2,000 feet higher than what is predicted on a globe or a flat Earth. And this has been used to try to argue against the methodology and say it doesn't work. It provides evidence for a concave Earth. That doesn't even make sense. It's like, so when the stars stopped getting occluded in the globe model and they added celestial refraction corrections, that they didn't say like, oh, well, maybe it's concave when it gets further over there. Like, no, that's just a rhetorical device deployed to try and discredit the methodology. The optical reasons why it was occluded at that elevation are that only happened one time. Like, we still need more data at distances like that. There could be something that occluded that, and it's not that dire. And in any rate, it's not sufficient to refute the hypothesis that the elevation angle should have been lower in the first place, right? So like, even if we throw that one out or whatever, it doesn't change anything. And then there was another observation at Blinn Mountain, which is said to match the globe explicitly. Now, if you go to observer location on that observation, the true position of the star intersects with the peak at the quote unquote globular time. But what isn't really announced in that is that to get that to line up, you have to have the angular difference that's predicted for globe drop be the same as the refraction correction. So in other words, if there's supposed to be like 22 arc minutes of angle missing from that mountain peak, and the celestial refraction correction is 25 arc minutes, well, congratulations, you're gonna cook it in the way that the angle is gonna line up with what the quote unquote globe would predict for the timing. But when you go to the peak, which is part of the process that we're doing, looking for that tangent to be valid for the angle to the peak and the observer, well, the position is no longer there. So it's like half of the method that was applied there to discredit it, and ultimately ended up proving the method is conceptually sound, because the physical occlusion process corresponded to when it was intersected for the observer with respect to the true position. So in all the other cases where we have 40, almost 50 plus observations where quote unquote celestial refraction is supposed to be the answer, well, that doesn't jive with the observation at Blinn Mountain. It completely falsifies the assertion that celestial refraction is responsible for all the other cases. It can't be higher and lower at the same time and not like that doesn't make any sense. All right, so I think that's all that I wanted to touch on. Mike, did you have anything, or Goose, did you have anything that you wanted to add in your recent travels?
Yeah, I got a quick little diagram I wouldn't mind going over.
Oh, awesome. Go ahead and screen share whenever you're ready, sir.
Okay. Can y'all see that?
Dude, look at you. We got your screen share timing down to 3 seconds.
Yeah, I made it easy on myself.
Dude, you're crushing it, bro.
Jam everything into Discord.
All right, what are we looking at here, big dog?
All right, I'm just going to go over it really quick. So we're looking at Pikes Peak. It's got a distance of 50.7 kilometers based on Movable Types website. We have a mountain elevation of 4,299 meters and observer elevation at 2,074 meters. We have geometric flat Earth predicted. So this is just rise over run. And then sitting below it, we have the geometric globe predicted. That's for the physical peak. And that's using this formula to do that. Oops. And then here we have, this is HD 217533, time of occlusion at 7:31:40 seconds, UTC -7, January 27th, 2025. This is its true star location here. True star angle based on stellarium at the mountain peak. Above it, we have the apparent star location. So this is just the true star plus astral refraction. And that's this formula here. They use this when you get below 0 to 15 degrees. You just plug in your
real quick
here.
Real quick, that's what I was talking about when I was referencing the refraction coefficients that they use to move the, to keep the star at the elevation needed so that the time makes sense. So like this 34.133 plus 4 point, like none of that has any physical bearing on like reality. Like none of that was derived off of like, oh, we went out and measured the temperature and pressure and this is what it would have to be. No. All computed and simulated out of a model so that will change the angle at that elevation so that it still makes sense for it to be on a globe, to be visible. Go ahead.
Mm-hmm. Yeah, and there's a whole bunch of them. You kind of just pick whatever one you...
Yeah, there's actually one for every 10 degrees of elevation that you could apply.
Yeah. So yeah, pick whatever you fancy. Where was that here? Yeah, so the parent star location, that's just true plus astral refraction. I got 2.78. Stellarium's 2.8. So it's just showing that's pretty close there. And then here, this is at HD 217533. That's the apparent angle from the observer at time of occlusion, and that's based on stellarium. And then, so what we're going to do is we're going to move to the globe position at the observer here. And how we got there, we took the apparent star angle. We moved 1 degree per 60 nautical miles. Where's that? Down here. Subtracted that to get our apparent angle of right here, 2.193. So you can see the globe apparent angle from the observer is right here. It's drawn right here too. So what that tells me is the globe position is even though like we have our this is the apparent, so at the mountain we have our apparent star up here, so this is where our light is zipping over top of the mountain using refraction. So even though we got our light flying over the top of the mountain, when we subtract, we go all the way back to our globe observer position and change our perspective on the star. And then look at that same star, where it's, trust us, bro, it's totally not the true light path being occluded by the physical flat Earth mountain peak. And that's it. It's this one here. What? Any question?
So what you're saying is the geometric relationship between the flat Earth prediction and the true position of the star, assuming that it's coplanar with the ground, is what was measured by using a timing interval. So like when the star was occluded and then referencing where that true position was, and the elevation of that came out to be the elevation that was predicted by a flat Earth. Is that what you're saying?
Yeah, that's this measure. Yeah, that's just that's not what I'm saying. That's just what the measurement is showing here.
Right.
Yeah. And then I think the reason why the globe likes going back to the observer position is because of this apparent star angle here.
Yeah, that's exactly what it's built on.
Up here, right? Like that's way up here. And all we're doing when we move back to the observer position, we're just changing our angle to our perspective on that star.
So if the sky is not coplanar, how does that change the observation there?
Sky is not coplanar. What do you mean?
Like you're saying, you said it was coplanar.
Oh, yeah, got you. So if it was actually like the timing that it gets occluded would be at a different time. It would be later because
Got you.
it would have to get lower.
Got you.
It would be down. Yeah, your timing would be down here. Or if you want to claim refraction, you'd have to take all this guy all the way up here and take him all the way down here.
Mm.
That's even more time.
Yeah, even more drastic. Okay.
So I think this is my best globe steelman I got on their position at the moment.
Very nice. I mean, that is what it was. That is how it was argued for, in perpetuity.
Mm-hmm. And it's just a perspective.
Yeah.
You're just shifting the globe. You're shifting the globe or the observer around by 1 degree per 60 nautical miles to get your apparent angle. And you're hanging out. For some reason, the globe wants to be over here, and all the action is over here. Like over here, you might as well just be taking your sextant, having a reading there. I don't know.
Mhm.
You're not self-theoing if you're over here.
Not unlucky.
You're just doing sextant measurements.
Yeah. All right, Mike and or Shane, if either of you are there.
Mike.
Well, there we go.
It's hard to beat Goose's presentation, and I don't really have anything new to add. I can't share a graph of what Goose was talking about for many stars, so I will go ahead and share that. All right, so I should have our graph shared now. And when Goose was talking about the elevation of the star with refraction added, that's the cyan line on top. And this is showing how much the refracted image is above where the globe Earth predicts the mountaintop would be, which is 0. The green line on the bottom is without refraction. So that shows how much below where the mountaintop is predicted to be that the star is located. So that was Goose's upper and lower star respectively. One right on the mountaintop is the red line, and you can see it's not perfectly on 0, but it's the one that's actually in between the two globe Earth predictions. So the both globe Earth predictions missed the mark by quite a bit, whereas the flat Earth predictions are really, really close to the 0 deviation line, except for the Lynn Mountain, where like Alan said before, that was specifically manipulated to give misleading results. So that's really all I have to say to supplement what Goose already said.
Awesome, thank you. And Shane, if you wanted to go over, so real quick though, so the refraction makes up the difference in predictions every time. Is basically what you found, right? Or it tries to. It overshoots it, but conceptually, what they're doing is trying to make up the difference, pretty much 1-to-1 with a refraction correction.
Exactly, and you can see they're reasonably close to hitting their predictions. They're just a little. In most cases, they're a little bit high. Occasionally, they can end up being a little bit low. In general, they tend to be a little bit high.
Yeah.
So, but It's all just a factor they're using. And this cyan line, that was done using G. Bennett's refraction equation. When you research this, what you find is the globe Earth people have like hundreds of different equations, and they're all a little different, and no two of them give the same results. So their predictions are basically all over the place. And quite often, what they'll do is they will pick whichever refraction equation gives them closest to the answer they're looking for. The big difference with the self-theo technique using the red line is that's just where it actually fell. There's no corrections of any kind. It was occlusion time. Where was it? And that's what the it's plotted the difference between what it measured and what was predicted.
Awesome. Thank you, Mike. All right. And then Shane, if you could show the new image you've been working on, kind of walk us through that a little bit to kind of help explain the process. I think that's a really nice way to summarize the argument, because it can be a little confusing when we're looking at some of the PDF material, and there's like 3 different trig formulas over here, 3 predictions over here. Let's see if we can make it a little more digestible here.
Right. Sure. Can you guys see my cursor when I'm playing this video?
Is that an ancient Greek?
Yeah, so I replaced our observer with the old Biastocles over here. So he's got no tools. The simplification I'm working with here is trying to reduce it to its base principles, because there's a lot of obfuscation going on and there's a lot of needless complication. And even though we've made multiple observations, each one is formulaically identical to this, right? So I'm just going to start. We have your flat plane prediction, right? So you have, the only thing you know is this guy actually has no Theodolite. He has an old school camera. Looks like from the 50s, taking black and white images, and he's got a chronometer right here. So these are his only tools. This is to show you there is no such thing as a celestial Theodolite, as some people have gotten confused on, right? It's not a real thing. It's a concept that Mike made up. It's made up. It's a made up method, right? This is what we're trying to explain. It's a conceptual method. And how we're using it is, the only thing this guy's observing is that this star goes behind this mountain. This is actually a video of the Pikes Peak occlusion, and here's the geometric setup, right? So he's watching this star go behind this peak. All he knows is the time. No idea what angle. This device doesn't take angles. He's got no tick marks. He's got no total station. All he does is make the observation. So what you do is, the only thing you know is the known height of this mountain and how high you are above sea level. So this is 4,300 meters tall. This dude's standing at 2,073 meters above sea level. You get basic arctan rise over run. So we do rise over run over here. So 4,300 minus 273 over 50,700. You get the arctangent of that. That's what gets our base 2 degrees 31 minutes prediction. That's where the flat prediction stops. That is our prediction. For the globe, it's more than that. You add first the geometric drop over distance for curvature, right? So here it is. The actual formula, 360 times the distance, 50,700 meters over 2 pi r. Related to degrees gives you about 27 minutes, 22 seconds. Now we're subtracting that from our flat prediction, and we're adding to that our G. Bennett celestial refraction with temperature gradient coefficients added in for below 15 degrees. Do the math out, that comes to about 15 minutes. So we're subtracting this, we're adding this. That's what gives us our globe prediction of 2 degrees, 17 minutes. Everyone with me so far?
Any questions,
Right, so,
lads? Now would be the time.
And if you disagree with any of this specifically, if you disagree with the math we just did, I'd want to hear from you right now. Because we had Ruhif, I think, approve this, and this is the actual method. Like, the only way out of this would be to disagree with this part, because we did this math, right? These are the metrics we're adding for Earth curve, and this is adding the component for refraction, and this is the actual globe Earth prediction, and this also is, if you remember, the stellarium prediction with atmosphere on, right? So this is the globe prediction. Either way we swing it, and this is the flat Earth prediction. Of course, we know the occlusion that this is happening at corresponds to this specific angle only, which is when we construct a new triangle because now we have a known angle, we have a known degree, right? So we just take our basic tangent function, which is again inverse of what we did in the beginning. We take our basic tangent of our known distance again, so tangent of 2 degrees, 31 minutes, and that's what gives us our actual height. That's what gives us back here. 2,226 is spot on. This is the correct elevation for the time of occlusion. If we apply the same method for our globe prediction, which again is confirmed, so 217 times 50.7 kilometers, the tangent of that actually gives us 2,025 meters, 200 meters off the actual elevation. So when Mike's doing graphs of elevation predictions, these are the discrepancies that we're predicting, that we're talking about, and this is the math to get it. So basic trig here, using basic refraction coefficients and basic Earth curve drop. If you disagree with any of these components, definitely speak up now. Otherwise, you'd have to argue that this dude would make a different prediction based on what he saw. That's the basic concept distilled to the simplest components.
Well said. Sorry, can you repeat that?
I said I don't disagree with the math, but I have a different question.
Oh, go ahead.
So if we're using stellarium, if stellarium gives us accurate position of stars with respect to time, where does stellarium say the star will be 6 hours after it's been occluded by the mountain?
Well, relative to that observer, probably some negative coordinate.
Yep. So in spherical coordinates, right, when you have a fundamental plane, because you're only making a hemispherical observation, then it would be represented with a negative z value, which is just meaning below the fundamental plane. It's the predictive capability is simply based on the circumference value and whether that circumference is the star traveling out and away from you to rise and set on flat Earth, or theoretically beneath your feet in the celestial sphere model, the circumference is the same, makes no difference. Anyway, about the celestial theodolite math, does anyone have any disagreement with the refraction coefficient? How about the Earth curve drop? Do you guys think it should be more?
No, I have a different question.
Please.
So does the star continue on its same path that it's as it's traveling down towards the mountain? Does it continue on its same path after it's been occluded?
Presumably, yeah. There's no reason to assume it doesn't.
So then 6 hours after it's been occluded, stellarium says it's going to be below my feet.
Yeah, did you not hear what he said? So Shane just gave you an explanation about negative coordinates and it being based off of the circumference, and whether or not it's arcing above you with your dome of vision and setting in due to optical reasons, or if it's setting due to physical curvature and you're rotating away from it because you're on a ball. The math to describe the two functions would be the same.
So physically though, where is a star physically?
Always above us, according to the measurements here.
Coplanar with the ground. It turns out everywhere you look, wherever, and only just because your model conceptualize it with a sphere of infinite radius as a model derived from zenith and ground conditions doesn't really mean anything, dude. It's not really a good argument. Please stop making it.
Okay, so you guys claim that since you just said it continues on its same path, right? Which is down. But it's not. Where is it physically? If it's not actually below me, which direction does it go once it's occluded?
The down that you're referencing is optical, right? It's setting into the horizon, so it looks like it's going down. That's an optical effect.
So a better question:
how does it end up behind me in the morning?
Well, like Shane was saying, mathematically representing it with negative coordinates, whether it's circling above you and it's setting due to optics, or if it's setting due to going around a ball and then rotating around on the other end, the mathematical function to describe that would be the same. It tells us nothing unique using the apparent position of a star. And also, real quick, if you didn't catch it earlier at the beginning, the angles and timing are all tied together with a fictitious observer to construct the model in the first place.
Okay, do you guys really? Okay, go ahead. I'm sorry.
Go ahead, dude.
Do you guys like honestly, do you really believe that a star is not below you once it goes below the horizon in stellarium?
You know, this is the same argument as the sun can't set, right? Like we believe it goes away and it takes its light with it and becomes you can't see it, right? And you say, well, no, it's beneath your feet. Let's just deal with the math right here, because people have said that there's a fudge factor, and that's the only way this works. If anybody could point out to me on this slide where the fudge factor is, I would be greatly appreciative.
So this is the problem I'm having with this method you guys have derived, right? It's pretty convoluted. I mean, I guess if you understand the mathematics, okay, it might work in certain circumstances. But my question is, if we're using stellarium, for the position of stars, stellarium tells me that the star 6 hours after it's occluded is below my feet. But apparently you guys, for some reason, either it's not going in that actual direction, even though it's continuing on its same path. That just doesn't make any sense.
Can you real quick before we continue though, can you repeat back the explanations that was given to you? Like, do you know what we said as like how it would function?
Yeah, you guys say negative coordinates, but that doesn't tell me physically where the star is.
No, it tells you exactly where it is because it's negative coordinates based off of time. It's just
where is that actually? If it's not actually below me, where is it?
Just above you, further away.
So which direction
it's
does
further
it go
away and it would
after
move around.
But which direction does it go after it's occluded? Does it go to the right?
All right, well, before it gets to the horizon to do the thing you're doing, it passes by the mountain peak at precisely a time that says the Earth is flat. Do you agree with that premise before it gets to the bottom?
I mean, I'm not really concerned with that. I mean, you can fudge
That's
that
the
either
whole
way
point.
you want using, but I'm concerned. You guys are like ignoring this huge thing, right? You're ignoring the fact that if you're using stellarium and you guys are saying that stellarium is accurate, then okay, then after the star goes below the horizon, it's continuing on its same path.
Listen, do you understand what it means that if whether or not it's below you or above you, the math function is the same? So just referencing the negative coordinate system itself, right? Just referencing that aspect of itself doesn't tell you if it's actually beneath your feet or if it's above you or further away. And that's something that you will have to understand or, come back to or something. But that's a pretty straightforward argument. Like, and you keep not acknowledging that. And if you're having trouble with it, that's completely understandable. But if you have another question or something else that you would like to move on to, I don't think we're going to be able to reach any sort of conclusion if we can't, if you can't fully acknowledge our side of what we're saying.
Okay. So my last question is, where the distance between the observer and the mountain, where was that taken from?
That was taken from either NOAA or what's it called? The Movable Types website, which uses a multitude of different calculations, one of which being the old spherical coordinate system, the old Haversine, right? So when you're using the spherical coordinate system known as latitude and longitude, which is defined by positions of the stars, you are using, a part of what of the trig on that, you get units of measurement in kilometers, which are defined from which are defined as a fraction of the coordinate system itself. So there's no, like, I see what you're trying to do, but like, you got to understand you're referencing a coordinate system computation with that references units of measurements derived from the coordinate system itself. So it's going to be internally consistent. So when we calculate the distance from the peak and the elevation and all of that checks out. Now, what doesn't check out is when we subtract what the globe predicts that the actual physical elevation is, and the star doesn't get occluded at that elevation. That's like that's what you should really, really be concerned about. Not the fact that we're using distances calculated based off of units of measurement with an internally consistent coordinate system to check and see if it's valid or not. It's like aspects of it are valid, right? Like we can reference distances and positions and all of that with the apparent positions of the stars, but is it physically describing the terrain that we live on? That is what's in question here.
When you say it checks out, do you mean like somebody measured the star, it checks out? Or so I'm just confused with the star underneath your feet thing. Like, I know Jeremy brought it up and other people keep bringing it up, but everyone kept saying that that an airplane is like referencing an airplane, but an airplane's moving, so obviously that's not in a fixed position. So
Can you
What? So
steelman the experiment first though? I don't think that.
well, yeah. So
I guess I'm
so one
confused.
second. The answer to this is actually two separate contentions right here. So his point of contention is that this is just like globe geometry. Where's the star? The other point of contention of of like it being beneath your feet was in reference to when your elevation isn't at like on the ground and you're looking at something that is also not on the ground. So the mountain that you're looking at is above the horizon and the star isn't setting into the ground or whatever, like you're not actually above it, it's optical. If you were to apply a dip correction, you would get a positive angle. We're just doing the raw angle because it doesn't matter. Like either way you slice the tangent, there's still the globe would still have a would need a bigger angle. Like it would need a bigger negative angle. Like so the only discrepancy there is a dip correction. It's not it's not
So
actually
the star's
beneath
not
you.
actually physically there. It's like an
No,
illusion or something.
no, because the elevation of the mountain isn't even physically above you either. Like it just comes out that way because there's no dip correction.
So no one disagrees with this example then, because we're going to go through this for all the peaks, right? This is the basic premise, right? Everyone says there's no fudge factor because no one could point it out. And if we're going to go on to what we think, below a star means conceptually, then we can all agree that this is in fact the correct math, the correct prediction, and the globe is 200 meters wrong, right? Everyone sees, everyone agrees.
Yep.
So when we say that we have, 43 different measurements, this is the process that we went through on the whole spreadsheet. This is what each data point represents. This is what the final graph represents, is these secondarily calculated heights based on the new angle that we derive from our triangle, right? Because again, once we get the angle prediction correctly by using Earth curvature drop and celestial refraction correctly, then this new angle based on a new triangle can give us the correct or at least the predicted elevation of occlusion. And this is why it's wrong, because it's 200 meters off. And every time we do this for every different point, it's at least 100 to 200 meters off. That's what the graph at the end represents. That's what the process that Mike put forth is actually doing. Before we go into any other stuff, does anyone have any questions on this? Because this is the process. This is the whole crux of it.
And if there are, oh, sorry, I didn't know that guy was talking. Go ahead, sir.
So there's not even Globers that understand this here.
Well, I noticed like with the globe people, whether or not they understand it or whatever, like that's fine. We want to help the flat earth community understand it more. So if there's any questions, definitely feel free to ask. Because I think this is one of the most significant proofs that the earth is flat, because it uses an external reference, the only external reference that we have to show that the geometry is coplanar.
Yeah, but you're ignoring a big part, but it's fine.
Who was that?
I said you're ignoring a huge part.
Gotcha.
This guy runs the flat earth server. He doesn't even understand our perspective position.
I understand perspective perfectly, but it's just the fact that once the stars occluded, we kind of forget about it, and it's not going on the same path. It's somewhere else.
Yeah. So if the star was occluded by Earth curve, all the celestial refraction corrections that they're applying to keep the stars coplanar wouldn't work. Like, do you understand the implication of what it means that the star gets occluded by the mountain at the time that the geometric position corresponds to when it's physically occluding? If that's true, if that's true, then what's your contention about the negative coordinates then? How do you not get
Stellarium? Stellarium works, right? Still for you guys, Stellarium works until the star gets occluded. After that, then what? That's the question.
It's just what?
That's all.
Yo, okay, so now, dude,
Well, I was just going to say it's a non sequitur to what this is, though. It's just a different topic. And on Stellarium, there's two settings. Right at the bottom, you see all the icons. There's an equatorial grid, which essentially treats the Earth as a sphere and puts the celestial sphere all the way around that sphere Earth, which is why you can like turn off the ground layer and you can see the stars underneath you. Or right next to that, there's the azimuthal grid. If you turn on the azimuthal grid, it treats the ground as a planar circle, and the stars do not go underneath the ground. So Stellarium has two settings. One of them is the azimuthal, which is essentially a geocentric planar Earth foundation. The other one is the equatorial. So B-Ball, when you're saying that, that's not true. Only the equatorial grid. Only the equatorial grid treats the stars as going beneath your feet, and it's a completely separate issue than what this is.
Oh, very good point.
The stars always go below your feet in Stellarium.
Well,
No, they do not. If you turn on the azimuthal, that is incorrect. If you turn on the azimuthal grid, they do not go under your feet in Stellarium.
And that kind of, hold on one sec. They're out of your vision. They're just further away from you. D3 already explained that. The equivalence between the two, it's identical. It would be mathematically represented by the same thing. There's no difference.
Which direction do they go?
East to west.
Once they're out of my
They
view.
circle around you. You see them arc across your field of vision.
Okay, so let's go to the equator. What if a star goes straight down to the horizon?
Same thing, dog.
Where does is it still going in that straight line? How does it come up behind
Bro,
you?
1 second before. Okay, so it's just math to the same function. There's literally no difference anywhere. Equator, North Pole, 33rd latitude, 38. That doesn't matter. All the same answer every time.
So this again at the equator, stars going in a straight line.
All right, I can't continue with that anymore. So, does anyone else have any questions?
B-Ball, it's just a separate point, or Earth is Life is your name on now. It's just a separate point. And as respect for the presentation, could you address this? Because this is the actual math for what the occlusion point is, what Shane's presented. I understand you have this other thing that you talked about for years. We could talk about that another time. It could be talked about now if these guys want to, but could you actually address the occlusion? So there's stars being occluded in this fashion. Do you agree with the math? And then do you agree that it's not matching the globe without those additional refractions? Like, do you have any actual response on what's being presented?
No, I only wanted to ask those questions. You guys can carry on.
I mean, they asked if anybody wanted to address the math and nobody did. So to try to force a room to talk about math that can't even be verified is kind of lame, that there are people trying to talk about this and you're like, let's not talk about it. We're not going to talk about it. We're just going to talk about math. I don't know. It just seems
when you say that the math can't be verified, it can because you can do the prediction.
You
1 second,
cannot measure the star. You can't.
Okay. Well, you're not going to talk over me. Number one. Number two, you can make the prediction, get the angle that it corresponds to with the time, and see if the occlusion matches. That's the whole point of it. So you can actually verify it, and it's also a triangle, so you can Pythagoras theorem verify it. It's the most verifiable thing that's ever been presented, and super repeatable.
Who verified it? The people on the ISS. They measured the stars with some.
When you say
no one's measuring the stars.
When you say measured the stars, what do you mean? All we have is an angle. We can have an angle.
Yeah.
That's all we need.
Yeah, you can have. Nobody's arguing that you can have an angle and that you can like guesstimate shit, but you need to admit that it's a guess and not claim that something is physically in the sky when it's underneath your feet and you can see the observation. And it's like 1 second you're contradicting yourself, saying that everything is that these stars are all in their fixed positions, and then at the same time you're saying that a horizon isn't fixed. And that there's other, it doesn't make any sense that you guys don't understand it and that you're trying to change the topic and say, well, we're not going to talk about it. Let's talk about math instead. Nobody's arguing your math, dude. Nobody cares about the math. Like the math. I mean, maybe some people care about the math. And so far, nobody in here has spoken up about the math. So obviously, if you want to move on. But it's kind of telling that you're like, we're not going to talk about this anymore.
We addressed it ad nauseum. There's no difference optically between the math that's represented when it says that the star is beneath your feet versus it continuing a circuit above you and it just being out of your vision. Those are the exact same thing. So when that guy wants to like ad nauseum repeat it, there's nowhere to go with it. The biggest point the big point that refutes the negative coordinate contention, the big thing that refutes that is these occlusion timings. If the Earth were a globe, or if it did correspond to to something going beneath your feet in that regard, then these timings would be different. So the fact that the timing isn't different, the contention that the coordinate system also implies that it goes beneath your feet is like a huge non sequitur.
So that whole thing that Jeremy was talking about with you guys the other day, that's just a non sequitur. It's just
Completely unrelated to the whole thing. Exactly. Yeah.
Like I said, when I addressed it at the beginning, I specifically said that these are two separate issues that we're talking about. One is that this guy was
we're not allowed to talk about that issue then?
No, I specifically pointed out both and told you the answer to it. The one is related to the elevation difference based off of a dip correction. It just gives you a negative calculation. It's not actually below you. So if we did a dip correction, we'd have a positive angle. It would be fine. Yes.
So is it like refraction? Like what is it specifically? Like I don't understand how you can say that that a star is fixed in its position, but then be like, oh well, it's not really under. Then it's not really an optical thing. Like
real quick, what do you mean by fixed in its position? The argument is that they move at 15 degrees per hour. That's not like when you say fixed in.
Your time, to be honest.
Well, 1 second. We still have to go through it, Shane. So it doesn't matter. So when you say that the star is like fixed, like that's not part of the argument.
Isn't that your guys' claim?
No, the claim is they move at 15 degrees per hour.
Okay, so the stars aren't fixed. So that star, it wasn't fixed. So that whole argument, I just totally misunderstood.
Yes.
I thought the claim was that the star was fixed.
The actual position.
The star is being occluded by the mountain.
I don't
So
understand.
So what's the difference between actual position and fixed? Like when I hear actual
okay. I got you. Okay, so the difference between true.
If I'm saying the wrong word,
no, you're good.
I'm
You're good.
sorry.
You're good. So the difference between true and apparent position, is that what we're?
Right.
Okay. I got you. Okay. So the true position of the star, right? A bunch of lads about 200 years ago all took zenith measurements at different locations across the Earth on the vernal equinox. And they used that zenith measurement to correspond that specific star to be at that specific point over the ground at a specific time. And then because it's a zenith measurement and it has the least amount of refraction, et cetera, and it has the most likely relationship to a ground position, right? The angle comes out to be like 89.99 or something like that, right? It's real close to 90. So they use that as their reference. And then from that, they go, okay, everything's moving at a uniform 15 degrees per hour. Now, this is not like so what they're doing here is they're now separating the apparent position from from the star that they saw and took their initial measurement, right? They're using that. And then they're adding 15 degrees per hour of motion across the sky for that in perpetuity, just always going at 15 degrees per hour. Now, the star that we optically see, right? The apparent position is always refracted. The light source is always moving. The distance between us, we never see the quote unquote true position. The true position is a calculated position. If you were to say hypothetically that there's a light source to the star and it's moving at that time that we took that zenith snapshot, the true position would be moving at 15 degrees per hour and the refracted position would always be a little bit ahead or behind depending on where you're looking at it from. And so when we're referencing the Shane, if you can pull up that slide again real quick, like at the beginning where it shows the angles and all that.
Yep.
Okay, so when we line up that calculated true position where they say it's going to be based on 15 degrees per hour, it'll be at this location. Right now, when you apply the celestial refraction corrections for the apparent position, it says it'll be in a different spot. But what's happening here is when we calculate what this angle would be for an observer X amount of distance away for a mountain peak that's X elevation high, that angle that we get is corresponding to that calculated true position, the same geometric angle on the top there. And then at that same time for the observer on the ground X distance away, the star suddenly becomes not visible. So the apparent position, goes out of view. And so what we're doing is we're recording the time in which the star is no longer visible, and then we're using stellarium to reference where the true position was, because all the true position is, like I said, it's basically just calculating out 15 degrees per hour with respect to where it once was on the vernal equinox. So stellarium is just like a real quick conversion tool to show that relationship. It's not like proof of the globe or anything indicative like that. All stellarium is doing is representing that 15 degree per hour relationship. And when the star is no longer visible, you hit your buoy negative coordinates and it goes beneath your feet, or it goes around in a circle, depending on whether or not you have the ASI grid on or the equatorial grid.
Okay, so did somebody actually physically take a picture of this
Yep,
star?
we have lots of videos of it happening.
This is real observation right here in the background.
So it's just refraction then. So it's
Nope.
basically like.
So if it was, no, sorry to cut you off. Okay. It's not the same as refraction, because what we're looking at here, right? See the star, we see it. And then when we don't see it, what we do is we have the time, because our recording device is synced to GPS time. So we can look up the time that the star is no longer visible. And then we can go into stellarium and see where it was at with the true position. And if that time matches, that time will correspond to an angle. And if that angle is the same as the mountain peak, then the physical occlusion between the lights, like the true position, considered the quote unquote source, is
so it's just based on stellarium's true position, right?
Yeah, which is just based off of the almanac and adding 15 degrees per hour.
Okay, so is there actual measured negative angle to a star, or is it just based off of the negative angle in stellarium of a star? Where would it be?
The separate issue, but the measured one, right, through the through the timing interval, is just calculated based off of the elevations of you and the peak that occluded. So it comes out negative, but that's not geometrically negative, because the mountain peak isn't higher than you are if you're higher than the mountain peak, right?
Right. So why can we see the star if it's negative, or whenever it's occluded if it's negative?
That's not what's happening.
No, it's not. There wasn't an observation where a star was occluded with a negative position?
No,
I thought that's what Mike said last week.
No, we're contriving completely different things. The negative is not a relation to the celestial theodolite experiment. You can figure out where down is, in a separate environment. But this observation specifically, when it goes behind the mountain, it's not actually negative. It's still above the horizon technically in both coordinate systems. That's not even what we're talking about. Behind the mountain, it still has to travel all the way back to the ground. So before it gets on that journey, we're going to do all of our presentation and our math and our commentary. Before that star even gets to the horizon, we know the Earth is flat. That's what we're trying to contend with.
I agree, but I'm pretty sure he said there was a negative angle from the observer of one of the stars last week.
Yeah, he did that to satisfy a ridiculous request, which again is unrelated to the celestial theodolite experiment and certainly doesn't change the results.
No, it was, but there's no dip correction, so it comes out negative. But obviously, physically, you're not lower than it. It's calculated that way because there's no correction for the elevation difference between you two.
I know, but why is it lower than the observer then?
Because the mountain peak is higher than the horizon. It's just optical.
Just optical.
These are flat earthers, by the way.
It's okay.
Yeah, but what? No, I'm just trying to understand how we can have, if it's in a true position, a true actual position, how it is underneath the observer.
The true position, my good sir, is just the calculated position of where it once was with respect to 15 degrees per hour. It's not like the true position. It's like I don't really understand how you're applying the true position aspect of it. Like it's not
like a geometric position.
It's not in a different position than like altitude wise than whatever the apparent position would be. Like there are the same. Like it's not like it's a
but
different.
There's got to be a reason why why you can visually see it below you as an apparent position. Is that reason because of curved visual space? Is that reason because of refraction? Or is that reason why can we see it below our horizontal? In geometry, if something is below your horizontal, that means it is below your horizontal.
You don't. The calculation comes out that way because you're not accounting for a dip correction because you're not on the surface of the Earth. So it's not a real negative angle. It's just
the observer height is not at the surface of the Earth. So anything below, you have to be on the surface to the inch to get that below that. So any observer on the surface obviously isn't at the same angle. Therefore, any angle subtending that would not be below anything. So it's an arbitrary question. But
it's a fair question. But if we applied a dip correction, like, do you understand that the angle would just be positive and it would be fine? Like, there's no issue. So
yeah,
it's
but
not,
what is the dip correction for? Dip correction is just for observer height.
yes, because you're not on the
still
surface
means
of
the
the
star
Earth.
would be going below the horizontal of the observer. Why there has to be a reason why a star goes under the horizontal of the observer. If that's refraction or if that's curved visual space, it should not go below the visual horizon of an observer, the level horizontal, without some kind of.
And yet the calculated angle does come out because there's a missing component of a dip correction. So, like, I don't know where to go from here.
Yeah.
So, like,
I think we broke this down well, though.
that is the answer, and I don't know how to better convey it to you.
So I think what we learned is that there is no fudge factor, and nobody has any idea where that comes from, and some people just repeat it. I think that's the takeaway for this evening.
Yeah, I don't know anything about a fudge factor. I wasn't referring to that at all.
No, you're good.
That's what we're disproving.
No, you're good. We're just laying out rhetoric for everyone.
Well, weren't you saying earlier that he didn't say it was a negative, but like Jane, didn't you say, or didn't Alan just say no? He did say it was a negative. So if he didn't mean that, why did he say that?
No, it was said. I was just contending the relatability because it's irrelevant to what we're talking about. And just because Mike added a separate data point to contend with a question doesn't mean that the whole experiment is about this negative angle, which is why everyone's talking about it now. So the whole conversation has shifted towards a nonsense point because all of this is correct. I mean, the flat earthers, you guys understand that the math is on our side here, right? Every single time when refraction is forced to be a prediction, they lose. That's the point, right? Before, they could just use refraction as an unfalsifiable blanket to apply to any and all observations, laser light, optics, everything was refracted, can never make any points. The Earth's a globe, right? With this, we make them predict it, and then when they have to predict it, it's wrong. And that's why they don't want to touch it, and they want to talk about everything else. I think everyone should
I understand that. And I'm just trying to be honest with the observations that if we're using the stars to prove the ground, and the star is below a horizontal that does not have an answer other than a dip correction, which I don't understand what that means, a dip correction.
This is ridiculous, dude. You guys are explaining to a glober and two flat earthers perspective. Like, this is not the presentation, dude.
Maybe just go over what the
listen, lads. It's all good. It's all good.
Maybe do the dip correction thing so he can understand that real quick.
Well, if you got cut off, let him finish. I don't know who got cut off, but if you got cut off, was that Jason?
Yeah, I'm just saying that the dip correction, in my understanding, is just the level above horizontal that the observer is. But if the observer sees something below his horizontal in the sky, then there's got to be a reason for that.
It's not below his horizontal. The dip correction, all it's doing is moving the ground to the observer, or you can think of it like moving the observer to the ground. Because the observer is not on the ground, you get this scenario where the mountain peak that is also not below the ground is above the horizon. And you get this illusion that gives you a negative angle. It's not.
Right, I understand. I get what you're saying.
If you understand that, though, then that's it. That's all that. I mean, there's like
right, but then we're no better than the globers that are claiming refraction when it doesn't suit them.
No.
When the observations.
No. One second. So here's why we're not, because if you don't include it, it's just a calculated negative angle, and it's still less than what they predict. They predict a larger one. So when you add the corrections, it's fine. Now, if you wanted to add their correction, which includes refraction, that's like, nullified in this, so it doesn't matter. But in the same respect, we could have a coefficient that raises the altitude to the observer, and it would be like, it doesn't mean anything that, like, so I don't, like, if you understand that part of it, to then turn around and be like, no, but then it is below your feet. It's just like I don't know what to do,
Right.
So it looks like
we say that
isn't reality things.
Right. And I get that. But whenever they say they can't use the 69 miles per degree, but they can't use it down at the horizon or a certain angle, then, that's their out. Like, So we can't use a star's true position. If it goes negative, that's our out. Like that's.
Oh, I mean,
That's
that
right
might
here. We use that.
that might be something that you have a problem with because of like your understanding in the matter, but it's not an issue for me or other people. So
We use the 60 right here. We add that in right here. That's where that Earth curvature drop.
Say one.
Dave? Was that Dave?
I don't know
Your
if you
light-
can hear 1 minute.
Dave, you're roboting.
He really wants to participate, but it sounds
Steve.
terrible. So
You want to know what else the Globers won't touch? Upward Earth. Just throwing that out there.
Just make it more retarded. Good job.
Easy, lads.
How about now? Am I
Yep.
better now?
Solid.
marginally, yeah.
Am I better now? Can I, good? Real quick. Yeah, it's just that I've heard Jeremy go through like, is it actual true position? I think the confusion is everyone thinks when anyone here says it's in its actual true position, that you're reifying the globe's true position claim of the star, which would be under your feet, right? We're not reifying the actual true position as if it were a globe and under your feet, but it's hard to get that out of your head when you say actual true position from Stellarium, which would depict it under your feet. But if you keep going on a flat baseline, the true position that Stellarium has it at will reflect the angles we're talking about when you get to that point. So if you keep going further and further out, you're going to see that those stars are still above you, but they looked like from a distance they were down below, just like we know the globe is taking advantage of perspective. The plane doesn't actually go below because it's above you, but it looks like it's coming up from the ground because of perspective and all those things that they've hijacked.
Can I ask a question about the experiment?
Does that make any sense? Did that help at all? I don't know.
I think so, Dave.
Perspective is
people
not
that
a
are-
good answer. Sorry. That's what everyone
You're
gets.
good. You're good. You're good. And then yeah, just real quick, like I said earlier, the true position, right? It's not, when I say true position, I don't mean like I know the elevation or anything like that. I just mean that is like they had a ground position that they can relate it to at a specific time, and then they're just 15 degrees per hour in and out, and then whatever angle it is based off of time with respect to that is
Right.
what
So it's just like-
what they're using. So it's not like I'm saying anything about like where the star actually is in reality or whatever. All I'm saying,
Right. It's where
is,
if in their model where it would be if everything was true in their model, if it was going around, that's where it would have to be, right?
No, it's where it is in the celestial sphere. It's a degree position in the celestial sphere related to 0 degrees of Aries. I think when people hear true position, yeah, they think that you're talking about like a ball of light up there and it's put into a water or firmament or like that's actually there. You could,
Yeah, that's not it at
Yeah.
all.
I started realizing that as we were going through this, and that's why it's like good to go through this. It's totally fine. Because this terminology and stuff that we had to figure out for all of this, like not everyone knows what what the true position means or like what it's in reference. So it's fine that these are coming up.
But it's not a measured true position, like even on a celestial sphere. It's just the timing measurement from a single location and then 15 degrees per hour after that, where it would be. Is that what you're saying?
Yep.
Yeah.
Okay.
Yep. Q-Up, did you have a question?
Yeah. So you guys are saying that it's matching the occlusion timing's matching the flat Earth more than the globe. I'm trying to figure out like what you mean by that. Like, does it occlude sooner than the globe thinks it should, or later? And does that help you figure out the altitude, or like how, like, does that help you kind of map out where the mountain is, like in the distance, like, and compared with like what the angle to the mountain would be on the globe model? How does that all connect?
Absolutely. Shane, if you could bring up that graphic again.
Oh yeah, I still got it up.
Okay, yeah. So the second part of your question was about like verifying the elevations and all that. Well, like Shane was saying earlier, once we have the occlusion angle, we can backwards derive what the elevation would be, and we can kind of verify those. So what we're doing with this timing interval and these angles is we're backwards deriving like the physical where the physical object would be in three-dimensional space, like this mountain, right? Is it going to be at an elevation that's where we're predicting, or is it going to be lower in reality for what the globe predicts? And if it's what the globe predicts, the star will get occluded at a later time because it has to get lower in the horizon to intersect with the mountain. And if the Earth is flat, then the star will get occluded at an earlier time because the mountain peak is physically higher than what is said to be.
Perspective I mean, don't they kind of do surveying and just incorrectly observe like perspective as Earth curves? So the mountain, so you're claiming perspective is not going to have the mountain as low as the Earth that the globe claims? You think? Are you saying?
Dude, I'm so glad you brought this up, because the hijacking of perspective is exactly why this method exists. So instead of measuring the angle optically, right? Because if you get a theodolite out and measure this optically, it's going to come out to be 217, which is or about 219, which is about what the globe predicts for the physical elevation of this mountain. But if we do this through occlusion timings, based on the premise that the occlusions are a physical process between a light source and a physical object to do the occluding, then we're going to have two different elevation angles in which we'll stop seeing the star. So if we know the time in which we're doing the recording, and we can sync that up to when we stop seeing the star, we could take the exact frame in the video that we stop seeing the star, add that to the time, and then that will give us where the star was at that time, and then we could look that up and reference all that. So we don't take an optical measurement, we take a timing measurement based off when we can't see the star, and then we look up, hey, hypothetically, if there was a light source here and it intersected with this object here, would we stop seeing it at this angle, or would it be at this angle? You know what I'm saying? So like that's the premise of what we're doing here.
Yeah, they're mutually exclusive, right? The flat happens to correspond with the so-called true, or just the one referenced in the almanac. If you were to look it up where the star was at the time of this occlusion, because the only thing you're observing is the time it's occluded, then you get this exact angle, which is why it corresponds with the exact height, which is why it corresponds every single time with flat, right? So they're two different predictions, mutually exclusive. If we did like a metaphor and there was a crime scene, there was one guy here at 2 degrees 31 minutes, and there was another guy here at 2 degrees 17 minutes. Which one was guilty? All right, you look it up. Well, this guy was, we had a camera over here. This is when it would happen. This is the match. This is the one that works. So that's why we say it's the flat Earth thing. The globe has to do all this crap all the time, and the benefit that we've been giving them is that after the fact, after we make an observation, they can just backwards derive this optic angle using their model and go, look, behold, it's a globe. To make them predict with it is the best way to do it, because then it fails every time, as we trying to show. And just because it's 200 meters off this time, it's 1 to 200 meters off every single time for 43 different observations.
Yeah, that's the key part, what you just said right there. Every time.
So there's no fudge factor. People say it only works because of a fudge factor. Everything that you need to derive this data is right here on this slide. There's nothing else there's nothing else that you need that's not here. Like this math comes out to exactly this, right? If you do it in meters, it gets crazy because you had to use, let's see, comes with the numerator is like 1,825,200 meters, and the denominator is like 4,700,000, 4,983, and it comes out to like 0.45 degrees, which you then convert to degrees, minutes, and seconds. But like this all works. This is all the same. And this is the same principle we apply to every single example. And none of this is ever refuted by the globe proponents. And this is what determines this. So all the other, objections and obfuscations and Jesse trying to make a simulator that adds refraction on both, and none of that addresses any of this. To address this, you have to address this math, and nobody has addressed it. Everyone has said that they agree with this. Ruhif, Jesse, everyone has said they agree with it, and then they tried to make other points, right? The only way you're going to change this is by addressing this. So the only conclusion is this is wrong and this is right. So basic trig means all stars are coplanar with the Earth.
Isn't the Earth curve drop math just an average?
Well, it's specifically tied to this unit of distance, right? So 360 times the exact distance we're applying over 2 pi r to get that. So that's pretty precise.
Did you calculate how much the peak would tilt as a result of that distance and under the globe model?
Yeah, so the missing elevation there comes from how much would be tilted away from you and not physically present.
2025 versus the 2026.
I'm just checking your math, and that
Or
looks like the drop.
2226.
Sorry, I'm just looking at the math. It looks like that's the drop, but that's not that's the drop, but not the tilt, right? Like if a mountain is sticking straight up and we measure it with a plumb under the globe model, it would tilt somewhat away from the observer and distort the model. Did you account for that, or do you think that that's negligible under these distances?
The observer is actually right here on the mountaintop, so negligible completely.
Can I respond to him? Yeah, I ask the go-overs about this all the time. Like, why aren't you using spherical geometry? That's what it would take. But instead, they use Euclidean geometry, even though they claim a spherical model, and they say that it's just so negligible, the tilt and what that would do to the angle, that they don't even account for it. But I do agree that they should be using spherical geometry in surveying.
But the observer is on the mountaintop, so there is no tilt from the mountain to the mountain, right? He's right here. This is where the observer is. That's why it terminates right here, and this is what the angle is calculated from.
I'm not sure I understood what you just said, but I am curious because the amount of error you have between these two is quite small. So if there is some distortion because of the models not being fully reified, I would expect relatively small amounts of error. I'm not saying you're wrong. I'm just saying the difference here is quite fractional.
Oh, you're good. So it appears that way, but the timing difference, 1 arc second, of angular I'm sorry, yeah, 1 arc minute of angular difference translates to 4 real life seconds. So the timing in which these occluded, so the difference between 31 arc minutes and 17 arc minutes, comes out to be like
14 times 4. Yeah.
Comes out to be about 40 seconds or so. So it's like in reality, the timing difference is very, very easily distinguishable. And then on top of that, once you have the time in which it was occluded and you reference that angle, you can backwards derive what the elevation was to see if it physically matches.
Yep.
The reason I ask is because once upon a time I had to make a globe visual simulation for one of my jobs. And one of the things I discovered was that I had to change the height of the mountains because they looked too tall in the distance and it was distorted. And I discovered that that's because if you lean a mountain away, perspective then reinflates it back up a little bit. That's all I have to say. Thanks.
Oh, you're good. So this is independent of how you optically view it, because the occlusion being physical, all we're concerned with is when we can't see the star, and then we reference where the true position of that star was at that time, and that angle is matching or closely matching the physical elevation that we calculated for what the peak would be.
Yeah, this is Glober's math. Like the predicted drop over distance, that's the math that the Globers give.
But my point earlier was that that's an average, no? How would you determine, like, if you did this same math in 2 different spots, wouldn't it be different?
Nah. So the difference between the approximation and at 50.7 kilometers, Shane, what was it, like 20 meters or something?
Yeah, you're basically talking about the difference between long distances. Like if it was like 1,100 miles plus, then you would use the formula that does the parabola. But since we're talking about these distances, you wouldn't use that. You would just use the 8 inches per mile squared.
Well, typically it's 360 over 2 pi r to get the drop, but we're specifically multiplying it times the increment of distance we're applying it to. So, I mean, you can say, sure, it's an average, but it's very specifically precise. Also, if you were to use the equivalent formulas, not 360 over 2 pi r, it comes out to precisely the same difference.
It's the same, yeah.
So no matter which formula you want to apply, which drop over distance formula, terrestrial or so you apply, it comes out to about the same amount. So.
Oh, Mike, if you're there real quick, if you want to go over the relationship of the 364 pi and converting it to radians and all that, like the approximation it's exact.
It's not exact, but it's so close to exact. only over extremely long distances can you tell the difference. So our farthest distance was Greenhorn Mountain, and that was actually North Peak. The videos labeled Greenhorn Mountain, but the stars were actually included just to the right of that at North Peak. But that's 130,000 kilometers away, so roughly 82 miles away. And at that distance, you cannot tell the difference between the precise calculation and this 360 times distance over 2 pi r approximation of that distance. And I actually plotted both ways for every star we've ever measured. And the biggest difference I found was in the neighborhood of 6 arc seconds. And
Oh yeah, that's like nothing.
yeah, it's nothing because we're rounding off everything. Usually, we're rounding things off to arc minutes. So we can't even see the difference between the ultra precise calculation and the extremely close approximation. And the nice thing about the close approximation is it's more relatable. You can see that it's basically 360 degrees over 2 pi r, and 360 over 2 pi part of that is just converting degrees to radians. So you're basically converting degrees to radians, dividing by the alleged radius of the Earth, and multiplying by the distance to find out what the drop is. And so for Pikes Peak, 50.7 kilometers away, it's 22 arc minutes, 22 arc seconds either way.
And the 2,073 meters, that's the observer height above sea level, or what is that
Right,
for?
that's the observer height above the reference geoid, because that's actually a GPS coordinate, and they do everything relative to a reference geoid.
Okay.
In practical terms, it amounts to almost the same thing as above sea level, but there's minor little differences. But it's easier to do everything and more accurate to do everything in GPS coordinates and meters, and so that's why the data is in the form it's in. It makes it easier to work with and more accurate for us all to verify.
So, quick question for you: if we did this observation during the daytime, and we just looked at, like, for example, in the little sketch you have up right now, if we just took a regular theodolite and we just measured the crosshairs to the top of that mountain that you're using for your occlusion peak, but we're just measuring the height during the daytime from the horizontal, what angle would you be getting there? Would you get the 231 or would you get the 217?
So I've actually done that under ideal conditions, and you will get the 2 degrees 17 arc minutes. And there's several important things to note about that. Number one, I did it under ideal conditions. So it was 0 degrees centigrade, 1 atmosphere, no wind, perfect infrared viewing conditions. And it's important to note that that was way, way, way beyond the stated accuracy range of the theodolite, because theodolites aren't stated to be that accurate 50.7 kilometers away. In fact, usually their stated accuracy is in hundreds of meters. And they all modern theodolites typically lose about 1 arc minute per 3.7 kilometers. I did try it with an ancient theodolite in the vicinity of 100 years old, and the ancient theodolite measured 2 degrees 30 arc minutes, and plus or minus 5 arc minutes was its tolerance. So it would have had to measure 2 degrees 25, 230, or 235, but it measured 230. So it was as close to the flat Earth prediction as a theodolite could possibly get. The modern theodolites, though, all measure in the vicinity of 2 degrees, 17 arc minutes, and there may be up to a few arc minutes of refraction correction necessary on top of that for less than ideal conditions.
See, aren't theodolites generally they're going to have an accuracy in terms of like, you know, plus minus 1 second or plus minus half a second. They're not showing a limitation based on distance. Maybe there's like a laser rangefinder or something on them that would be like a limitation on distance when using the laser rangefinder to range find, right? Because these are total stations have like multifunction. But when you're
So
just using the
you made a
theodolite
misstatement. Before you go on, you made a misstatement I'd like to correct. You're confusing precision with accuracy. Modern theodolites tend to have about, depending, the ones in the $1,000 to several $1,000 range typically have a precision of plus or minus 1 arc minute. The tens of $1,000 ones, they may have a precision down in the 15 to 20 arc second range, but that's the precision. If you read their specifications carefully, that precision is only valid within a few hundred meters. So after that, they're inaccurate. So everybody who's saying they measure the elevation of a mountain accurately do not understand the difference between precision and accuracy. And I'm sorry for interrupting you. Go ahead.
I still don't understand because a theodolite is measuring angles, and the limitation of your precision is going to be based on the accuracy of that angle measurement. What does distance have anything to do with it?
So this doesn't have anything to do with an optical measurement. So we're doing timing intervals and referencing where the star would be with respect to 15 degrees per hour with respect to where it once was on the vernal equinox. So we're not doing optical. We're actually doing timing intervals to confirm the physical intersection, which is what causes the occlusion.
And in this breakdown, right, we're not even using a theodolite. We're using an old, you can use a telescope. This guy's got a camera. In the simplest version, he's got a camera. All he can see is the star being included. Has no idea what angle it is. So,
but you still have to have the light propagating or not propagating from the occlusion point to the observer 50 kilometers away. How is that not an optical measurement?
1 second. Someone's hot micing. Rich.
Rich.
You're hot micing, sir. Go ahead and mute.
Just singing a tune?
Just humming away. Just to be true.
Oh. All right. That's an inside joke. That's all right. Anyway. Yeah, Jake, what about the actual occlusion timings of the star being occluded by the mountain peak in that timing interval there? Because we can argue optics all day. People have for years, right?
this guy has no idea what angle this is because all he can see is that the star is being occluded. So this observation has nothing to do with the angle, just that it was occluded. From this observation, we get a time. That time corresponds to our predictive trig angle. That's all we're looking at here. So this guy looking over here has nothing to do with it, which is why refraction over here doesn't really take into account. All of this is from here to the star, which is what we're calculating, which is where the mutually exclusive part lies.
But what is ticking off your timing that you're using as your timing point is the signal, no signal of that star being occluded, right? If the star,
oh, I got you.
You know,
one second.
And that in its essence is an optical. That's an optical signal. I mean, I know you guys are trying to say this isn't an optical measurement, but it is, because it's an optical signal that tells you
check
light
it out.
or no light.
So check it out. We take the frame in which the star is no longer, like when it's not visible, and it's not when it, like not even when it's a little dim or fade, when it's just not there anymore, right? That exact time, we pause the video, look at what time that is, and we add that to whatever time we started the recording of the video, and that will tell us, and then we could take that time and then go into Stellarium and look at where that star was with respect to its true position at that time. And it just so happens that when we do that, it's more corresponding to the flat Earth elevation angles.
By a large amount, 200
So
meters.
is it your contention that even if there was a great deal of refraction, that wouldn't, no amount of refraction would ever change the signal, no signal that the observer is seeing to do their timing based on, stop the timer at no occlusion.
No,
based on
that's
the frame.
that's specifically not my point. My point is that there is a specific amount, and that will correspond. That still corresponds to a different time, because a refracted image can't refract or can't block refracted light. So the occlusion has to be done at a physical time, and even if there's refraction in between the star and the mountain peak, there's still going to be physical occlusion timing. It can't make up the difference 1-to-1, because that's not even what happens when we measure it with this, even though it's not very precise. But with a point source, it's not going to be 15, 30 arc seconds below something, like physically. That doesn't track. And we
have
get
you,
some.
have you ever seen?
Go ahead.
Sorry, go ahead.
Have you ever seen Rob Skiba's sun setting explanation on this little diorama with a Fresnel lens?
I have, and the difference between that is we're talking about a star, which is about an arc minute, maybe an arc minute and a half, depending on the star. And what Skiba was showing was like an image that has like a large image, and then like certain aspects of it are refracted over, not the entire thing.
Wait, what's an arc minute? I'm sorry. When you say an arc minute, what are you describing as an arc minute?
Arc minute is an angle.
No. But what did you say is an arc minute?
I don't remember. What did I say?
You said to rebuke Rob Skiba's thing where he showed a light source setting because of refraction.
Sorry. Yeah, I got you. The angular size of the star is about an arc minute, or like an arc minute and a half, versus what Skiba was. What's that?
A star is not an arc minute. A star is a point source of light. If you have a very high power telescope and that can accurately measure into the sub arc second range, it's still going to be sub an arc second. Like if you go.
Yeah, so check this out.
It's not an arc minute.
So check this out. What we're looking at on the screen here, you see that video playing in the background behind the diagram? That's an actual video of a sea star recording an occlusion. The width of that screen is 44 arc minutes across. That star that's traveling across the screen is about an arc minute big. So it is a point source. I completely agree, but I'm saying that little dot there can't be, that little dot can't be 22, 23 arc minutes below that and then still be above it. Like that's preposterous.
I still don't see, if Rob Skiba has demonstrated that refraction can make a light source disappear, why can't refraction make a light source disappear behind your mountain that's occluding the star?
Which refraction video of Skiba's are you talking about? Because I'm thinking of the one where he has the sun, the little diagram of the sun, and he's pulling it away, and like that's a big image of a thing. Like, so we're talking about different angular size in relation to the refraction and how much is visible. So
he's showing a light source. He's showing a light source that's above the horizon, and by moving the Fresnel lens's focal point forward and backward, he shows how the sun is able to set behind and be occluded from the observer, even though the sun is still above the horizon.
I'd have to see the video.
Right, but we're talking about a mountain that you can clearly see in the video.
So one.
Well, the mountain is irrelevant, right? I mean, if
no, I see what you're saying.
If a Fresnel lens can occlude a light source due to refraction, then
can you send me the video?
Oh, okay, I'll try to find it.
Because I can't.
It's an old video. Rob Skiba's passed now, so it's an old video from like 2016, maybe.
All right.
Yeah, correct. So in the diagram that Daza just showed, this observation doesn't negate refraction. Your conclusion is our premise. Even with refraction, there's still a physically different occlusion timing. That's what the whole that's what the whole introduction of this was, going over that.
Was there two people talking?
No.
Yeah, I think Electric was talking about a different thing.
Who? Who? Oh, sorry, I must have him. I'll mute for a second. My bad.
From his house to the peak, the star occludes at 2 degrees 31 minutes. Are you saying that it's the same elevation angle from the peak to the star? 2
No
degrees and
one,
31 minutes?
no one is predicting anything to do from here to here. The prediction all has to do with from the peak. We're predicting from the peak. The baseline of the triangle terminates at the peak. The actual elevation is from the peak. The mountaintop is what's doing the occlusion. This is what we're doing. So this is what the calculation is deriving. It's from this peak to the star. That's what this angle represents. In fact, the tool that this guy has doesn't even know how to do that. This is just an old school camera he's using and a chronometer.
Okay, so they measured with a theodolite from his house to the peak. The elevation angle of the mountain was 2 degrees and 19 minutes, right?
No, nobody measured anything from the house to the peak. He looked at he looked at the star being occluded, and he got a time. That's all that this does. He looks over here and he gets a time. Didn't record an angle. Can't see an angle. Has no idea what angle this is. Only knows is the time this star was occluded. That time corresponds to a true position at that time, which corresponds to this angle from the peak, which corresponds to what we predicted using our trigonometry of the flat baseline extending to the peak. So the only thing we're comparing is the true position and our calculation that we determined based on basic trig. So from here.
I really want to ask Dr. Mike, wasn't somebody at your house with an actual theodolite measuring an elevation angle to the mountain, Pikes Peak?
Somebody claimed to be. Somebody later denied it. In any case, that all of that obfuscates the real issue here. The whole reason I came up with this concept of a celestial theodolite is nobody could agree on what the measurement was from my house to the peak. Um, it depends on refraction. It varies throughout the day. They're using devices that are way, way beyond their range of stated accuracy. And the celestial theodolite is a way to eliminate all the problems so that you don't need a device that takes an actual angular measurement. It doesn't matter if there's refraction, like Taylor's excellent video showed. The laser light will go right through the refracted image, but it can't go through the real knife. And so the peak similarly is stopping the starlight as it tries to go through the peak. And that's how we know the instant the peak intercepted the starlight. And from there, it's just a simple matter of seeing what does the nautical almanac say was the elevation of that star at the instant the starlight disappeared. And that's what turns out to be 2 degrees and 31 arc minutes for Pikes Peak.
Stellarium says that the moment it would have been occluded would have been 2 degrees and 18 and a half minutes. And then
So that's an error.
the
That's an error. Stellarium, we've got the data in actual captured, and I can look it up for you. And it seems to be saying in most cases that angle is about 2 degrees 33 minutes, 2 degrees 34 minutes. So it's typically an arc minute or two high, but it's so far away from so far away from 2 degrees 17 minutes. There's no contest. We knew that it was the flat Earth angle.
But no, there's no angle over here.
Stellarium says the angle from your house to the star being occluded at that time is 2 degrees and 19 minutes, right?
Now I know. Now I know what you're doing. You're telling me a globe Earth angle, and that's the other problem with theodolites. They have to be from the location of the observer. By watching the peak occlude the star, you eliminate all of that nonsense. And like Shane said repeatedly, with just a camera and a stopwatch, all you have to do is see when did that star disappear. You've got the timing. And now the only thing that matters was what was the elevation of that star at the peak that did the occluding. Whatever's happening at the observer is irrelevant, and you're stating a number at the observer's location that doesn't matter.
Completely irrelevant, right? This is what we're comparing. This is the mutually exclusive part.
So you're not so you don't actually have an elevation angle with a theodolite. No
Well,
one
that's why
ever
the
actually went to your house with a theodolite. Why was that being said?
no angle over here. See, this diagram has every piece we need to make our outcome, right? This is the predictive comparison. So there's no angle over here because nothing is compared to it. It's not used. No one measured it. It doesn't matter. It's not used in the math at all. So all that matters is this angle over here, which is why we're trying to talk about do you disagree with the Earth curvature drop that we're using?
I'm concerned about the elevation angle in real life with the theodolite, the elevation angle to the mountain peak. That's what I
Okay.
want to know.
Okay, right. So hear me out. If you look through a theodolite during the day from Mike's house, it'll say about 217 to 219, depending on the weather, right? Our point of contention is that the compression that makes that mountain peak appear so low is optical. Now, the globularists say that it's physical and it's due to Earth curvature because the mountain peak is tilted away from you, therefore it's at a physically lower elevation. So using a theodolite, we would not be able to differentiate between the two predictions because optically they would be the same. So what we're doing by referencing the physical occlusion with respect to the calculated true position of where the star is we're drawing this geometric relationship here that says, hey, we can't see the star anymore. What angle was it again that we can't see it? Or what, I'm sorry, what time was it that we couldn't see it? Oh, let me look up stellarium. Okay, it was this time. Okay, with refraction off at the mountain peak, stellarium predicts that it's at 231. Okay, so if the star's true position and the mountain peak are at 231, then there should be no physical relationship between me not seeing the star at that same time, because if that were true, then I could draw a tangent from me to the peak and then from the peak to the star, and it would all show that coplanar relationship.
Okay, I'm gonna keep it super duper like blatant with Dr. Mike. My understanding is you borrowed someone's theodolite to actually measure an elevation angle.
Correct. Yes. That's our premise.
And that elevation angle was 2 degrees and 19 minutes.
Yes.
Okay, so therefore it doesn't match the flat earth trigonometry prediction, right? So you must be invoking some effect to make the mountain appear lower than the flat earth trig prediction, right?
Yes, it's optics. When you're looking through it, the compression is optical. Whatever you want to call it. Whatever mechanism optically you would like to call it, that difference, right, is the same as what you would call Earth curvature.
Okay, so you invoke curved visual space in between Mike's house and the peak to correct for the elevation angle being too high. It's displaced too much vertically.
No.
From the
No, low.
Not at all. No.
You don't invoke curved visual space.
Not for the way that you just worded it.
Not for this. Not at all. Nope. We're only calculating this angle right here, right? So we're not concerned with what it appears to be from here. We're only calculating the angle from the mountain to the star. That's what we're calculating. That's what the comparison is for.
Calculating it with time. Hold on one second. Calculating it with time. Right? Because if you know what time it is, you know what angle that star is relative to you. Right? Like, do you agree? Like, you understand that part, right?
Yes.
Okay, cool.
I want to know.
So, stop. So if you understand that part, then the optical measurement, right, it's not a factor.
It's irrelevant.
Looking through the theodolite doesn't matter. No.
It's not relevant because you're going to get different. You're going to get different measurements.
Please. Thank you.
All right. So it's not once it's not.
Okay, you're not letting me respond.
Well, I was trying to respond and then whoever chimed in, so I was waiting. Good. Go ahead.
So the elevation angle from his house to the peak measured with an actual theodolite to be 2 degrees and 18 minutes. The flat Earth trigonometry prediction from his house to the peak is 2 degrees and 31 minutes. So you have to invoke curved visual space downward. You're saying that's what happens, correct?
No.
Okay, so what is causing the displacement of the angle?
Optically, right? I would say curved visual space is causing that compression.
Perfect. Now I have something else. So now let's put our observer at the peak, right? And you're looking at the elevation angle of the star. In stellarium, it says the elevation angle would be 2 degrees and 31 minutes. What happened to your curved visual space? Why is there no vertical displacement anymore?
That's our premise, bro. The true geometric position is aligned up at 231 at the peak. There should be no physical relationship to an observer on the ground. The star should still be visible for that person. It should still be refracted up above it, if I'm not mistaken.
So the elevation angle of the star from the peak to the star in the stellarium is 2 degrees and 31 minutes, correct?
Yes, sir.
Right. So because it matches in stellarium, you say I don't need to invoke curved visual space anymore. You just invoke it wherever it's convenient.
You're conflating different arguments. So check this out, my dude. Let's start over from the beginning, right? No curved visual space yet. We're just two guys trying to figure some stuff out with old Pythagoras' theorem, right? So we got an observer here that's 50.7 kilometers away from this mountain peak. He trigs out what the raw flat Earth prediction would be if we don't adjust for any elevation drop over distance, right? And then after we get our flat Earth prediction, we subtract what the globe Earth drop would be, right? So now we have two different angles to reference. Then we go into stellarium. We go to the coordinates that describe the mountain peak, right? We're now at the mountain peak in stellarium. We look for stars that are that line up with that angle, and when they do, we just write down their time, and then we on the ground record the stars setting into the mountain peak. And when we no longer see them, we write down what time that was, and then we look at our video file. And we say, okay, well, our video file was created at this time, so we know when the video started. We add the time at which the, in seconds for when the star was occluded, and then we look up stellarium and we see if that angle matches the globe Earth prediction or the flat Earth prediction.
No matter how much you talk about this angle, it doesn't matter. It's never used. It's not part of the prediction or the math.
Yeah, we're not concerned with the theodolite measurement, right? Because the occlusion is a physical process between the physical intersection of the peak and its relative elevation to the observer. So if the Earth is a globe, then there's going to be elevation missing from it, which means that star, to get occluded with respect to its true geometric position, has to get lower. So that's all we care about. You're talking about an entirely separate thing and then kind of conflating them. And I don't think you're doing it on purpose, but it's just
like there's no theodolite here and there's no measurement here. This is all we need to. No, there's only a camera. He's only recording the time of the occlusion. Nothing else. No angle recorded. Nothing from that is relevant or used in any way.
You're contradicting what you just said. Dr. Mike just said he used the theodolite to measure an elevation angle to the peak from his house.
Listen, the process of using a real theodolite, right, is different from using the timing interval conceptual celestial theodolite. We're not contending that the optical angle when using a actual theodolite should be X, Y, or Z. Right.
So then why, when he asked him and said, hey, did you have someone brought a theodolite to your house? And he said, yeah. So it was it wasn't?
No.
Wasn't
so,
okay.
Hold on. Ruhif had said that he was going to send out a surveyor to confirm the elevation angle to the mountain peak, because Mike, using an antique theodolite, said that he measured 231. And then he later borrowed his brother-in-law's more updated theodolite or whatever, a more modern one, and he got 219 or 217 or whatever the globe predicts, right? So That's all the theodoliting that's been done.
So there was a
I would-
physical theodolite or whatever there.
No,
right?
there was a measurement, but it has zero relevance on the data. So that's the important part.
They didn't use measurement.
There was no theodolite. That wasn't true.
No, there's no theodolite in this example with the math that we're going over in this presentation. How we described it when we broke it down was specifically to get rid of the obfuscation layer that you just added back on by trying to make it about this optic angle. This guy doesn't have a theodolite. He's able to deduce all of the same and come to the same conclusion with the same measurements by just making an observation of the time of occlusion and then going through the same process with the trig. At no point is this angle added to any of this. At no point is this angle used in any of this predictive math. So to continuously say that it's about this angle means that you agree that all of this proves the Earth is flat and you're desperately flailing around.
Okay, so
No,
quick
the
question.
point that I really wanted to make was that you have to invoke curved visual space for the cause of it not matching the flat Earth trig. Then when you move to the peak and you want to get a time of an elevation angle to a star, that it matches the flat, and you say it matches the flat Earth prediction from the peak, right? Is that what you're saying?
No, when you say it doesn't match the flat Earth prediction, right? We're not calculating what it would optically be, accounting for curved visual space or anything like that.
I'm curious.
It's just the raw elevation of what it would be if the Earth's flat.
When you start with the star that you're monitoring on the video above the before it's occluded, what are you using for its angle of elevation and azimuth as the starting point? Are you measuring that directly with a telescope, or how exactly are you measuring
time?
The time, but okay, but where are you getting those coordinates from as to what its elevation, altitude is, and its azimuth at that time where it's above the horizon and visible as your starting point to start your timer? Where are you getting that angle from?
We don't need a starting angle. We can derive, or we can look up what the angle is when it gets occluded.
Well, we do get the starting bearing. We get the starting azimuth, right, from the block type or whatever we do for the final bearing to get the coordinates. We definitely need that, but that's just from the peak. So.
No, but like that's what I'm saying is.
Oh, all the start.
To get the final altitude that it's occluded at, you're using time from some starting point and then subtracting the 15 degrees per hour from that time, right?
Stellarium does all that for you. That's
okay,
what,
so the stars above the horizon, you're using stellarium's altitude and azimuth as your starting point for your timer, and then from that starting point, you're subtracting the time multiplied by the 15 degrees per angle to get your final occlusion, right?
Well,
is that essentially it?
No, that part's already done. Where the star is in Stellarium has all that information updated every second when you click on it, like a little stat sheet. So the azimuth, bearing, all that, all updates every second as the star moves. So,
Okay, so
whenever
that's what you're using as your starting point for your timer, correct?
From the second that we don't see the star, we know what time it is because the video file that created has the timestamp of when it started, and then when we look at the video, we know how many seconds it was until the star got occluded. So we add those two together, and then we could go and look at the time in Stellarium and see where the star was at that time, and get all that info.
Please hold on, Jake. Just give me 1 second. Okay, so how do you know the elevation angle to the star from the peak?
Time.
Are you using Stellarium?
Yes, and referencing time.
What is that elevation angle?
231.
That's with refraction turned on, correct?
No, it's off.
Refraction off from the peak, the elevation angle is 2 degrees and 31 minutes.
Yes, sir.
So now you don't need curved visual space.
We're not doing an optical comparison. We're seeing what time corresponds to what angle that we no longer see the star. So curved visual space isn't important in this because only the occlusion will be done by a physical process.
All right.
So in other words, if the elevation of that mountain isn't what we calculate it out to be, then the timing in which we no longer see it is going to be different.
This elevation is what that would relate to, right? Because this angle corresponds to a different elevation. When we make a second triangle over here and we use our known angles to deduce the elevation, 2 degrees and 17 minutes comes out to this different elevation, 200 meters below. So that's why it's relevant, and that's why it's mutually exclusive from this point. We're actually calculating the same for both up to here. Both models use this whole part the same, because remember, the globe prediction starts with the flat baseline. So we calculate the flat baseline, the globe takes the flat baseline, subtracts the drop over distance about this much, and then adds in the celestial refraction about this much to come back to this different angle. And that different angle, what gives us this elevation, which is wrong.
Wouldn't the flat Earth trigonometric prediction be much greater than 2 degrees and 30 minutes from the peak to the star?
No. It'd be exactly that.
Why wouldn't it change? You're getting closer to the star.
There's a flat baseline.
The distance to the star, the elevation angle should increase. You're saying it matches from his house and the peak.
We only calculated it on this triangle right here. Yeah.
Based off of the time that we no longer saw it, which
it's only
which if you drew a tangent, it would complete this geometry right here. That we're
the indirect reference at the end is that the stars are coplanar, so that we can assume that this could be the same angle. But nobody measured that. That's not contingent upon the measurement or the outcome or the results. That's an indirect reference at the end. That's what you can infer based on the results.
Does anyone know the flat Earth trigonometry prediction for the elevation angle of the star from the peak?
It's exactly 231.
It's on the diagram.
With
that's the same exact elevation angle from his house. Why wouldn't the elevation?
Boom, bro. That's the point. The conclusion.
Closer to the target.
Not listen, yeah. Now listen, my man. Listen, my man. If you go to where the observer is doing the recording from, Stellarium predicts that star is well below the peak and already been occluded. So it can't also do that, be not visible, and then also still be visible and occlude to complete this geometric relationship that we're drawing. The contradiction that you're trying to rectify is exactly why we're flat earthers now.
There is absolutely nothing that could explain an elevation angle not changing when you change the distance to the GP of the star.
Ooh.
It's the same angle.
So because the thing that explains it is that the geometry of the Earth is planar. That explains it pretty well.
Yeah, if I'm on a flat surface and I measure an elevation angle to a tree and it's 2 degrees, when I change my distance to the tree, it's going to change the elevation angle. You guys are saying that the elevation angle is 2 degrees and 31 minutes at his house and at the peak.
No. So if you used a star to be occluded by that tree to confirm the physical elevation difference, like that'd be one thing. So like you're only half committing to what we're doing here, and like this is kind of getting a little not going anywhere. Yeah.
Real quick, I just want to say this. Electric. The reason.
Why wouldn't it matter that he actually did use a theodolite and measured the angle to not match the flat Earth prediction?
Hold on. Can I address what you said? Can I address what you said?
Actually, hold on.
I'd like to address what you said.
You didn't hear what I said.
No. I want to address what you said earlier. You said by moving the distance to the peak, like if you change the distance, you're going to change the angle. But we're talking about a star, okay? The angle to the star remains the same, hence it's planar.
It doesn't remain the same. The flat Earth trigonometry prediction for the angle to the star from the peak is not going to be the same from his house. You're changing the distance.
There's no mark of that. There's no angle to the house. See how it doesn't matter? That's not what it's about at all. The celestial theodolite method is calculating based on the peak. So if you're not going to engage with the method, then that's a whole different argument, right? If you're going to invoke this angle, that's a whole different method. No one is using this observed angle. No one has written this down. This isn't present in the prediction, in the math, or anything. I don't know how many times you can say it. You'd have to address this right here, the globe corrections to the flat baseline. This is where it has to connect for any of this to make sense. Everyone keeps ignoring this is very telling.
No, dude, you just said that he didn't measure an angle from his house to the peak with an actual theodolite. Why are you saying that? Yes, he did.
Yo, so not only did he say that, okay, listen.
You already did say that.
Two separate arguments, bro. The optical theodolite measurement and this are two different things, right? Because the optical theodolite could be explained by Earth curvature or some sort of optical compression, curved visual space, as you said earlier. Right, so we can't know for sure. But what we do know is that occlusion processes are physical. So there's going to have to be an intersection between a light source and the physical peak, so we can trig out what the actual physical elevations would be. And so we can differentiate. We can use this method to differentiate between the visual space and the spatial field.
Here's the
Pardon
part
me.
that.
Hey, Electric.
Here's the part that I.
No, hold on, Jake. Jake, let's deal with this point completely. Hey, Electric, have you taken the time to perhaps quantify your assertion? How different is the angle? Did you ever get a grip on that figure or even how to compute it?
Yeah, I made my point very clear. I'll repeat it since you think I don't
Well, yeah,
understand.
but is your point numerically significant? Is your point numerically significant is the
You
question.
need to actually listen, okay? According to Dr. Mike, somebody did in fact bring a theodolite to his house and measure the elevation angle of the peak. It's 2 degrees and 19 minutes. The flat earth trigonometry prediction, 2 degrees and 31 minutes. You guys are saying that the flat earth trig prediction from the peak to the star is also 2 degrees 31 minutes.
Where do I say that?
And listen, in no instance ever on Earth has changing the GP of the observer not affected the elevation angle to something.
Where am I referencing the angle from the house? Where is that needed again? Could you point out where it's used in the math over here to get our prediction?
That's the flat Earth
So listen,
2
listen.
degrees and 31 minutes from his house to the peak.
Listen,
That's the
Electric.
prediction for the height of the mountain.
Electric. Pay
You
attention.
can keep saying that
hang
until
on.
you point it out. You're not saying much. Like they've already
hang
told
on.
you they're not using that.
Yeah, and on top of this, real quick, Electric. Man, I forgot what I was going to say now. Give me 1 second. Oh, right. So if the optical theodolite measurement were corresponded to the physical elevation of the mountain in reality, right? Then the time that star gets occluded would be a later time in the evening because it has to get lower to get to that delicious 217 that was measured optically. That doesn't happen. And the fact that doesn't happen means that the optical measurement that was done with the theodolite from Mike's house doesn't describe the physical elevation of the mountain, because otherwise there wouldn't be an occlusion. All right. So now that that's cleared up, we're done talking about the optical angle. We don't care about the optical angle. Optical angle matches what the globe predicts. Yes. It also matches what a flat Earth would predict with a curved visual space or some other mechanism of optical compression. So
can I ask a question about that? Sorry, I've been waiting for Electric to finish.
Fuck, dude. Real quick, I'm trying to wrap up. We've been live for 2 hours. Just give me 1 second because we're about to wrap up, and you can end on your question. Just give me 1 second.
Sure. Thank you.
So regardless of whatever was measured optically, right, the timing difference in which the star isn't visible actually decides the physicality of the situation. That's what gives physical meaningfulness to this, because the process of occlusion is with respect to source and physical object, not refracted object. That's why we kept playing the video at the beginning of the knife in the glass of water and the video from Goose, etc., in the occlusions of Jupiter's moons. So if you can't get behind that, that's all good. Now, we're going to move on to, what was your name again, sir?
Karen.
Okay.
Karen, yeah.
But before he goes, can I just say, but did Dr. Mike say that there was also, he used like an old style theodolite and he got like 230?
Yes.
And then the new style gave like 219 or something. So what do you think what do you think the difference is there? And that's the one question, but also Electric. I think what they're saying is that, if I'm correct, is that the celestial theodolite method does not involve using a theodolite from the base. However, Mike may have done it as an additional thing for testing and so on.
Curiosity.
I think that was,
For
yeah,
funsies.
curiosity.
you.
Yeah, I just wanted to make sure that was correct, if I'm correct on that. And then, yeah, so what is the difference between the older style giving the 230 versus the newer style giving the I thought it was 19 or something. Yeah, so what are your thoughts on that? Why were those different? Like, is there something with the new one? There's something with the new ones that are adjusted.
Are you asking
differently?
electric? Who are you
Yes.
asking, Gio?
I guess
so
Dr. Mike, like,
if he's here.
whoever, because like the old style,
Okay,
they said gave 230.
I'm still here for a few minutes. We're about to hit sunset here, and I'm going to have to put lock dogs up for the evening. But it's actually the big discrepancy between theodolites and the fact that even modern theodolites vary all through the day, and they're constantly giving different measurements. That's what made me realize refraction and other factors are the big issues. And so the celestial theodolite was specifically designed to eliminate all those negative factors that impact terrestrial theodolites, where the old ones give different readings than the new ones give different readings for different times of day, different temperature, different pressure. Their measurements are all over the place. The celestial theodolite, now that we've got quite a few measurements, what we're finding is they're repeatable. They don't care about the temperature. They don't care about the pressure. They don't care other than the fact that it's got to be after sunset when you can see stars. Other than that, it doesn't care what time of day it is. So they eliminate all the problems we experience with both ancient and modern optical theodolites. And it was all those discrepancies. The important thing to understand is all those discrepancies with physical optical theodolites that led to this concept of just find out what time a peak occluded a star, and then reference the nautical almanac to see what was the elevation of that star at the time of occlusion, and then you can use that to calculate the peak. And on all my spreadsheets, that's what the graphs do. They compare the measured altitude to the predicted altitude. So basically, the real measurements, whether I did it or whether somebody else did it from my yard, are all irrelevant. And that's what motivated this much more accurate method of determining the same thing without any optical effects, without any refraction effects. And it's turned out to be far more repeatable than we ever could have predicted from the beginning.
All right, great. Yeah, thanks so much. Because that was a
Nice.
question I had earlier. Yeah, I wanted to ask a little bit about that. Really appreciate it. And it makes sense too over those grand distances too. You know, the huge distances being involved, which is a factor, of course, when you're just aiming a theodolite way off in that distance. So yeah, all the discrepancies and issues, which we've talked about for years, those issues. So yeah, that's what I wanted to ask. I know you guys are trying to wrap up. So was Karini Dave or whoever else wanted to? But yeah, go ahead, Karini, if you were gonna ask something. Go ahead.
Sure. I was just interested if you're positing some sort of visual distortion or other effect that's changing the optical properties, and you've just taken an exhaustive record which you think has a timing reference unaffected by those optical properties. Can't you expect then to observe some sort of nonlinear motion or acceleration of the stars? With respect, you could literally prove that the thing you're positing exists if it's there by gesturing to the data. You should have a nonlinearity in the motion of the stars. And if it's not there, then I don't really know how to reconcile what you're saying. It's very confusing to me what the geometry would look like.
Well, it's already not there because the 15 degree per hour relationship only holds between the angles of 25 degrees and like 70. And even in that, there's, celestial refraction corrections that are derived as coefficients, which are just curve fits to make real world observations fit what the globe, what the globe predicts. So there's already nonlinearity there. So we're good to go then. High five, brother.
No, I'm saying like,
welcome to nonlinearity, brother.
It is crazy. Have you ever seen those celestial correction tables? They're massive.
Well, on that note, we're going to go ahead and wrap up. Is there anything else you wanted to add, Karen, or are we good?
No, I just think you would see it in the video.
We do. Isn't that crazy?
I just wanted to ask Dr. Mike before he left, or is he gone already?
Should still be here, maybe?
I believe he left.
Oh, yeah, he bounced.
Okay.
Okay.
Never mind then.
All right, cool.
Well, I think we made lots of progress tonight. That was good.
Yeah, it was.
Yes, sir.
Thanks everyone for showing up. Sorry if things got a little heated or frustrated during the thing, but you guys know how it is.
Yeah, I'm gonna go. I'm gonna go chill on a mountain above a star for Jeremy's sake. Thanks, Jeremy.
I consider myself an ambassador to Globe Earth, so if you guys have any questions, you can always ask me.
Nice, dude. Dude, a Globe Earth ambassador is exactly what's needed. We have a Flat Earth ambassador. We should get you guys to. Oh, no go. I like his enthusiasm though.
Yeah, it can be misleading.
Hey, quick question. Has someone kept track of how many times you've repeated the same exact explanation? I'm just
19
curious.
tonight. Yeah, I was counting.
It's
How many?
Lily.
I made up a number. It felt like it was 19 times we said it though.
All right, boys. We're gonna go ahead and wrap up.
I
Thanks
had a-
everyone
I had
for
another
tuning
quick-
out.
Oh, I'm sorry.
Yeah, let me wrap up real quick and
Yeah, go ahead.
all right, I'll be back. All right, everyone. Thanks for coming out. Thanks for continuing the saga and joining us on this eventful night. I think we made some good progress here. We will return in the morrow for a presentation that has not yet been constructed. So stay tuned for that, for the normal 8 p.m. Easter Cosmology roundtable discussion. And then Tuesday, Man of Stone will be presenting on Globebusters his Shadow Sets video. So check that out. We'll see you guys tomorrow. Oh, and also on Thursday, we're hanging out with the Clubhouse lads and ladettes to do a little Celtheo update over there. So we're going to be hitting those guys up and talking over there on Thursday. So Tuesday, Thursday, and Sunday, we're all booked up. So check us out there. See you guys tomorrow.